In this video, I want to show you where the formula for the product moment correlation coefficient actually comes from. And I'm going to do that via an example. So I'm going to go through this the long-winded way. Now, you will either be able to do it on your calculator, but more than likely have to use summary statistics. So you won't have to do it longhand, like the way that I'm showing you how to do it here. Okay, but this is just to kind of like get a grip on what the formula is and where it comes from. So here I've got some data. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bits of data, and I've plotted it on here. Okay, so essentially what I want to do is I want to find a measure of how correlated this data is. And what we do is we essentially go through quite a similar calculation to how we derive the standard deviation formula. So it's very similar to that. So the first thing that we're going to do is we are going to calculate the mean of the x's and the mean of the y's. So I'm going to get x bar, which is the sum of all of the x's divided by n, and I'm going to get y bar, which is the sum of all of the y's divided by n. Okay, so that's the first thing I'm going to do. So 1 plus 2 plus 2 plus 4 plus 4 plus 6 plus 8 plus 8 plus 9 plus 10 is 54. So 54 over 10, so 5.4 for x bar. And for y bar, we've got 10 plus 8 plus 9 plus 3 plus 6 plus 6 plus 4 plus 7 plus 2 plus 2, which is 57. So 57 over 10 is 5.7. So we've got 5.4, 5.7 as the mean of the x's and the mean of the y's. And what we're going to do is we're going to plot that point onto the diagram here. So I'm going to do that using, I'm going to make it obvious that it's a different point by using a different colour. So 5.4, 5.7. So I would probably say somewhere there. Okay, so this is my mean point. Essentially, it's the mean of the x's and the mean of the y's. And I am going to now divide my graph up into 4 regions. So I'm going to draw a horizontal line through that mean point, like so, and I'm going to draw a vertical line through that mean point as well. So something like that. Okay, right, and I'm just going to call this region 1, that one region 2. The numbering doesn't really make a whole lot of difference, but it's just so that we can talk about them more easily. Region 3, and that one's going to be region 4. Okay, so what we're going to then look at is we're going to measure how far each of these data points are away from their mean position. So we want some kind of measure of that. Now, when we were doing the standard deviation, we would look at x take away x bar. Okay, so if we were looking at the horizontal distance, so if we looked at this point, for example, and we looked at the horizontal distance, then this point has an x coordinate, and I could work out that difference by doing x take away x bar. Okay, and the point and the value that I would get would be positive when we're in region 1, because we've got a larger value take away a smaller value. So each of these data points would give me x take away x bar, which would be positive. So I do x take away x bar. But we also want to take into account the differences in the y's as well. So we're going to have the y distance, so the y value for each of those coordinates, take away the mean for y, so y take away y bar, and when I do that for any point that is in region 1, I'm going to get a positive value, because we've got a larger value take away a smaller value, so it would be positive. So essentially we would get a positive value times by a positive value, and so that would be a positive value. Okay, so we're going to do that for each of the 4 regions. Okay, so I'm going to work out what this is for each of the 4 regions. So we're going to have x take away x bar, y take away y bar for that region. We're going to have x take away x bar, y take away y bar for this region, and we're going to have x take away x bar, y minus y bar for this region as well. Okay, so let's look at that region 1 first. So I'm going to need x take away x bar, and I'm going to need y take away y bar. Okay. So we're going to be taking 5.4 away from each of the x values. So minus 4.4 for the first one, then minus 3.4, minus 3.4, then we're going to have minus 1.4, minus 1.4, then we're going to have 0.6, then we're going to have 2.6, 2.6, 3.6 and 4.6. And then for y take away y bar, we'll have 10 take away 5.7, so that's going to be 4.3. Then 8 take away 5.7, so that's going to be 2.3. Then we're going to have 3.3. Then 3 take away 5.7, so minus 2.7. Then we're going to have 0.3, 0.3. 4 take away 5.7, so minus 1.7. 7 take away 5.7 will be 1.3. 2 take away 5.7 will be minus 3.7 and minus 3.7. Okay, right, so we've got those. Okay, so for region 1, so which ones are in region 1? We've got 6, 6 and 8, 7. So 6, 6 and 8, 7. These are the 2 that are in region 1. Okay, so we're going to have the 0.6 times by the 0.3, so 0.18. And we're going to have the 2.6 times the 1.3, and I'm going to add those together. So we should get 3.56. So essentially I'm going to add up those values in each of those cases. So I'm going to get a total for each of the regions. So that region 1 is going to give me 3.56. Okay, for region 1. Right, now if I go into region 2, I've got the 110, I've got the 2.8, the 2.9, and I've got the 4.6. So, and that one. Okay, so those are the ones I've got in that region. So I'm going to do minus 4.4 times 4.3, and then plus minus 3.4 times 2.3, and then plus minus 3.4 times 3.3, and plus minus 1.4 times 0.3. So minus 38.38. Now, should it be really relatively obvious that that should be a negative answer, right? Because when I do the horizontal bit of x take away x bar, the x value in each of these points is always less than the mean. So I'm doing a smaller number take away a larger number. And so x take away x bar will always be negative for region 2. But y take away y bar, because the y values are larger than y bar, will be positive. So you have a negative times a positive. So that will be negative, and you're adding all the negative numbers together. So you should get a negative result here. Okay, so let's look at region 3. Now we've only got 1 point in region 3, that's the 4, 3. So that one is by itself. So we've got minus 1.4 times by minus 2.7. So that is 3.78. So 3.78 for that region there. Now, is it a surprise that it is positive? Well, we know that x take away x bar, because we've got a smaller take away a larger value, will be negative, and y take away y bar, because now the point is below y bar, that will also be negative. So you've got a negative times a negative result, giving you the positive value. So if we now look in region 4, we've got 3 points remaining. We've got the 8, 4, the 9, 2, and the 10, 2. So we've got that one, and that one. So 2.6 times minus 1.7. We've got 3.6 times minus 3.7, and 4.6 times minus 3.7. Minus 34.76, so minus 34.76 goes in there. Now, are we surprised that that's negative? Well, we've got a positive value times a negative value in each of those cases, and so we would expect a negative result. So, it's probably no surprise then that we've got the majority of the data in the bottom right-hand corner, so region 4, and in the top left in region 2. And the values that you're getting are negative. Okay, you're going from top left to bottom right, you're getting negative results. Okay, so negative correlation, that seems to be working out for us. And those in region 3 and region 1, they are positive numbers and hence positive correlation. So what I'm going to do is I'm going to add all of these together now. So if I add all of them together, I refer to that as SXY, the sum of all of the x take away x bars times the y minus y bars. So let's figure out what that would be. So we have the minus 38.38. We've got add 3.56, add on 3.78, and then take away 34.76. And we get a grand total of minus 65.8. Okay, right, brilliant. Now what is this telling us? Well, not a great deal, it turns out. It's negative, and so that means it's a negative correlation. But how strongly correlated it is, we can't really tell. Now, there are 3 problems with this, with just leaving it as it is. The first issue is that this doesn't take into account how many bits of data there are. Now, you might be thinking, well, surely it did, because we divided through by 10, we worked out the mean that way. But think of it like this. If I doubled all of the data points, so if I, instead of having just a single 110, I had 110 and another 110, and I had 2828, 2929, 4343, 4646, etc. So I double them all up. If I plot the scatter graph, it would look identical to this. It would look identical because each of these data points would now represent 2 data points. Now, would that scatter graph be any more spread out than my other scatter graph? than this one? Well, no, because they look identical. So surely how correlated the data is shouldn't change. But if I have doubled up all of the data, all of these values are now twice as large as they were previously. So actually what I would get for my SXY is minus 131.6. Now, if I'm comparing these two sets of data, I should get the same correlation value or coefficient. But actually I'm getting something different. I'm getting something that is a much larger and more negative than this one, which you might then infer means that it's more negatively correlated, but it's not. So that's the first problem. Okay. Now, the next problem is it hasn't taken into account how spread out the data is. Okay. Now, what you could do is you could take one of the data points and just move it. So if I move that data point and I drag it up here so that it remains on the line of best fit, so essentially it's as spread out as it was previously, okay? But in the terms of how close it is, remember we're looking at how close it is to a straight line, okay? So if I just drag one of the data points along the straight line, if it was on the line of best fit, then it shouldn't change how spread out the data is. But it will have a big effect on this value, because the distances between x and the mean will grow, okay, in that direction and in that direction. So, in the x direction and in the y direction. Okay, so those distances will grow, which mean when I multiply the two values together, it will get much larger, and so this value will get much larger in the process. But the data is no more spread out away from that straight line. Okay, so from that correlation. So it doesn't take account of how many data points there are. It doesn't take account of the spread. And the last thing is it doesn't take account of the units. Now, at the moment, I've got these as like single ones, okay? If instead I had, let's say these were meters, if I turned it into centimeters, then we would have 100 centimeters, 200, 300, 400, 500, etc. Okay? So each of these would be multiplied through by 100, and then each of these would be multiplied through by 100. And then when I multiply those numbers together, this value here, when I've added them all together, will be much, much larger. So, but that hasn't changed how spread out the data is. So it doesn't take account of the number of bits of data, or the spread, or units. So this isn't good enough as a measure of correlation. So how do I deal with it? Essentially, I need a way of scaling it down. Okay? I need a way of scaling it down. And in order to do that, I need to scale it in both the x and the y direction. So, I'm going to get rid of this now. I'll leave that there. So the product moment correlation coefficient, R, is found by summing together all of the x take away x bars, y take away y bars, and then I need to scale it down. Now, I can't just do the sum of the x take away x bars times by the sum of the y minus y bars, okay? Scaling it in that way. Now, I can't just do that, and the reason for that is essentially I'm going to get some positive negative issues coming through, it may well be that that cancels out the negativity that's in, or the positive or negative that's in my top row. Remember, that is identifying whether it's positive or negative, so that's fine. But if I start doing this, I might end up essentially having a negative on the top and then dividing through by a negative, and my result becomes positive. And I don't want that meaning a negative correlation, right? So I have to divide through by something that I know will be positive. So what I'm going to have to do is, for each of my x take away x bars, I'm going to have to square it and then add them together, because I know that that will be a positive result. And for each of the y minus y bars, I'm going to square it and then add them together. Okay? But now, the problem with this is that I'm now dividing by too much, because I'm dividing by 2 squared values. So the kind of like the order polynomial, essentially, in the numerator denominator are not balanced. So to make sure that they are balancing, that I am scaling it correctly, I need to divide through by the square root of this. That's how you counteract it. So what I need is x take away x bar squared and y minus y bar squared. Okay, right. So we've got 19.36, 11.56, 11.56, 1.96, 1.96, 0.36. Should have been able to do that one. 2.6 squared is 6.76. 6.76. 12.96. And 4.6 squared is 21.16. Okay, then we've got 4.3 squared, 18.49. 2.3 squared, 3.3 squared, minus 2.7 squared, that'd be 0.09, that'd be 0.09, 1.7 squared. I think just be glad that you won't have to do it this way in an exam. And then the last one, 13.69, 13.69. Okay, right. So let's work this out then. We've got minus 65.8 in the numerator. Okay, now I need to add all of the x take away x bar squareds together. Lots of opportunities to go wrong on this. 6.76 twice 12.96 plus 21.16. Right, I get 94.4 for that. 18.49, 5.29, 10.89. And 74.1 there. Right, and then finally 65.8 divided by the square root, 94.4 rather, times 74.1 is minus 0.7867 to 4 decimal places. And so that value is identifying that we've got moderately strong negative correlation. Okay, and so that is my PMCC for this data. Now, as I identified, we refer to that as SXY, that is the shorthand notation for this. For the sum of x take away x bar squared, that is SXX. So we have SXY in the numerator over the square root of SXX times by SYY. Okay, and that is my formula for the product moment correlation coefficient, and that is how it can be calculated. Now, this formula by itself, as you can see, is quite cumbersome to use because I've got to calculate each of the values for x take away x bar squared, y bar take away y bar squared, add them all together. It's not the easiest thing to work with. So we are able to write it in an alternative form, which in the OCR MEI Further Maths formula booklet, it is given to you in an alternative form. And I'm going to show you how you can get there, how you can derive it. You won't need to be able to derive it, and I'm just doing those videos just for interest's sake. But we use an alternative version which allows us to use summary statistics rather than the original raw data.